My name is Reich, and today I'll be presenting my ECE 106 project. The goal of this project is to apply our knowledge to solving real-world engineering problems. We're going to create a sensing device that uses a capacitor to complete a certain task. We'll go into quantitative detail and qualitative detail. We will be covering over 4 specific parts of this project. The first part being the description of the project, giving a general overview of what we're going to do and how we're going to do it. The second part is a theoretical analysis of the sensing device. We are going to create equations of capacitance and understand how it works in theory, and then we're going to do an experimental analysis of how our device works. And we're going to conclude this presentation with practical considerations and limitations of our device. We are going to begin by describing the functionality of my project. The purpose of this project is to act as a temperature sensor. Essentially, it is a capacitor-based system that uses parallel plates that monitors the dielectric constant and how that influences capacitance. We're going to use water as a dielectric, and the dielectric of water will change as temperature changes. Therefore, the capacitance is dependent on the dielectric, and the dielectric is dependent on temperature. Essentially, the dielectric inside will change, and so will the relative permittivity, and we're going to monitor that change in relative permittivity. Practically, this device can be used as an AC or heat regulation device. We could install it in every room of a house or building and report to a central system. This device will maintain and monitor temperature within a household or even in residential buildings. This will keep a building at a constant temperature, and the practical uses of this is it helps a building or household from installing multiple different AC or heat units when it can have one that will maintain a constant temperature. This saves time and money. Now a brief onto how our capacitor works. Essentially, water will be our dielectric, and we're going to be measuring the different states of water and its influence on the dielectric constant. You may be wondering, why are we using water as a dielectric? Essentially, water has a very good range for the dielectric constant depending on different temperatures. At 0 degrees Celsius, the water's dielectric constant is about 88, and at 100 degrees Celsius, the water's dielectric constant is about 55.8. Furthermore, we're going to be measuring capacitance. As you can see on the screen, capacitance is a function of epsilon, or relative permittivity. And in our situation, since water is a dielectric, water will be dependent on temperature, so capacitance is a function of relative permittivity, and relative permittivity is a function of temperature. Furthermore, we're going to be using a voltage divider to measure the capacitance within our system. We're going to use one capacitor with a known capacitance, and then we're going to have our capacitor, and we're going to use the voltage divider formula to determine the capacitance of our capacitor. So a huge part of our analysis is determining the relationship between capacitance and temperature. We're going to use a linear model and a linear regression to determine the relationship between capacitance and temperature, and we're going to use an exponential model to determine the relationship between capacitance and temperature. And we're going to see whether the linear model has a better regression to fit, or the exponential model has a better regression to fit. We'll go more in detail about this in the future using Desmos. Now on to the capacitance geometry and the detection process. Essentially, we're going to be using small parallel plates as the shape of our capacitor. Since they're going to be located in every room, we have to optimize the shape of the parallel plates to be able to fit in the corner of every room and not take up too much space. While we do that to minimize the size, we also need to maximize the sensitivity while also being subtle and not making huge changes. The second part is there's going to be water in between both of our parallel plates. So that means we need a material to bound the water on the outside so the water does not leak out of the parallel plates. So our intention is to use a material such as glass or polystyrene to prevent the water from leaking and prevent it from evaporation. The reason why we use glass and polystyrene is that they have low dielectric constants, and that won't influence the capacitance calculations since the fringe fields will be going through these materials on the outside. And the last part is the detection process. As we mentioned in the previous slide, we're going to use a voltage divider. And to use this voltage divider, we're going to use an Arduino and a voltmeter to calculate the Vout value. Also, we might be considering differences between AC and DC currents. Now we're going to begin our theoretical analysis. Before we begin our theoretical analysis calculations, I need to state some of the assumptions made for our calculations. Some of the bigger assumptions that we made were ignoring the fringe fields, A being significantly larger than D, the typical parallel plate assumptions, assuming that they are ideal parallel plates. We're going to assume constant pressure since that has an influence on the dielectric constant. We're going to assume that water is pure, so that means the dielectric constant is going to be similar for all the water at the different temperatures. And we're going to assume that all of the parts in our circuit work perfectly. For instance, our voltage is outputting the proper amount of voltage that we're asking it to output. Now we're going to move further into deriving a theoretical model. First, we know the general capacitance formula is C is equal to A times epsilon over D. In our specific situation, we want capacitance to be a function of epsilon, so we have indicated that within the brackets. So C, a function of epsilon, is equal to A times epsilon over D. However, in the previous slides we mentioned that our epsilon is going to be a function of temperature since we are using water. So that means we can further expand and say C is a function of temperature, which is equal to A times epsilon, which is a function of temperature, over D. However, this brings the question, what is epsilon at T? Going further into understanding this question, we see epsilon at T is equal to epsilon naught, which is a constant that we have learned in class, times epsilon r times, which is a function of T. Epsilon r is a dielectric constant of water, which is temperature dependent. However, now you may be wondering, what is epsilon r at T? We're going to be extracting data from a research paper that analyzed relative permittivity at water of different temperatures. You can see the APA citation of the article right here. We're going to graph the points from this article and complete a linear and exponential regression analysis. On this slide, we have shown the values we have taken from the dataset provided by the article. For instance, at 0 degrees Celsius, the relative permittivity is 87.74. At 20 degrees Celsius, the relative permittivity is 80.103. And at 100 degrees Celsius, the relative permittivity is 55.72. In this diagram, we can see that there is a huge change from 0 degrees Celsius to 100 degrees Celsius, which makes our results a lot more noticeable. Once again, the link is at the bottom of the screen. As you can see in this picture, we plotted all the values in Desmos and we completed a linear analysis and an exponential analysis. Currently, both of the analyses are overlapping each other on the screen since this is relative permittivity versus temperature, and you can see the E-plots on the bottom near the x-axis, which just shows how off the values are from the exponential and linear regression lines. Moving forward, we're going to show the relative permittivity versus temperature using a linear function. So on the left on Desmos, you can see y2 is approximately mx2 plus b. This is our linear function. We can see that the regression of this value is relatively strong, being 0.9961. That is a very high regression. Typically, a perfect regression is at 1 exactly. And we can see the residual plot on the bottom as well, and the residual plot does not vary by too much. So this is a very strong model to use. And you can see it is represented by the function epsilon r at T is equal to negative 0.31938 times T, which is temperature, plus 86.6438. However, it brings up the question, can we improve our approximation of these points to get an even stronger analysis? And I was looking at these dots and I noticed there is a curve in it, and that brought up the idea of an exponential analysis. On the next slide, we can see that we use an exponential line to fit the curve. On the left side on Desmos, you can see we're saying y2 is equal to approximately n times e to the power of mx2, and we can see that the regression squared value is equal to 1 exactly, which means the exponential model fits this model absolutely perfectly. This exponential model for the dots are represented by the function epsilon r t is equal to 87.7211 times e to the power of negative 0.00453711 times T, which is temperature. And this is the model we're typically going to use moving further in this project. As we mentioned in the previous slides, the exponential model fit all of the data points the best. So we've used Google Sheets to create a more formal graph of all of the values, and we put in an exponential line as shown by the function above of 87.7 e to the power of negative 4.54 times 10 to the negative 3x, and it has the regression squared value of equal to 1 exactly. On the vertical axis we have relative permittivity, and on the horizontal axis we have temperature. Thus we have derived our formula for ER at t. So going back to our original question, we can answer what is epsilon at t. So we stated that epsilon r at t is equal to 87.7211 times e to the power of negative 0.00453711 times t, which is temperature. However, this is a mouthful to say, so we'll simplify it by a few terms. I graphed both of these functions in Desmos, and there is minimal changes, so it is fine that we use a simplified version. So the simplified version is epsilon r at t is equal to 87.72 times e to the power of negative 0.0045 times temperature. And thus we can conclude that epsilon at t is equal to epsilon naught times 87.72 times e to the power of negative 0.0045 times temperature. And now we know what epsilon at t is equal to. And now we can go back to the original question we're asking about deriving a theoretical model. So we know that capacitance as a function of temperature is equal to A times epsilon as a function of temperature divided by distance. And we recently discovered that epsilon as a function of temperature is equal to epsilon naught times 87.72 times e to the power of negative 0.0045 times temperature. Combining these two equations, we can develop capacitance as a function of temperature is equal to 87.72 times A times epsilon naught times e to the power of negative 0.0045 times temperature all over d. Moving further, we have to optimize our capacitance equation. So on the previous slide, we derived the capacitance equation that is on the screen right here, C at t. And to optimize this equation, we have to find the rate of change of capacitance with respect to temperature. While we're doing that, there is a new term that we're defining, sensitivity. Essentially, sensitivity is the rate of change of capacitance per unit temperature in our scenario. We want to find the highest sensitivity value to optimize our capacitance. So that means S at t is equal to dC at t over dt, where t is temperature. On this slide, we have our calculations to determine the value of S at t. So essentially, we have our capacitance equation on the first line on that page. And since we know that S at t is equal to dC at t over dt, we take the derivative. In the first line, we show that we're taking the derivative of the capacitance equation, we factor out the constants, and we're left with the derivative of e to the power of negative 0.0045 times temperature. We take the derivative of that and simplify the equation, and we end up getting sensitivity as a function of temperature. This will be written on our next slide. And thus, we have concluded that sensitivity as a function of temperature is equal to negative 0.394771 times epsilon naught times A over D. And all of this, these are the constants, times e to the power of negative 0.0045 times temperature. Now it goes back to the question of how can we optimize capacitance. To optimize capacitance, we want to increase the magnitude of sensitivity as much as possible. To increase the magnitude of sensitivity, we would want to increase our value of A, since that is in the numerator, which would increase the magnitude of sensitivity, and we would want to decrease the value of D, which would also increase the magnitude of sensitivity. The third point I wrote note, we cannot decrease our T, since that is a quantity we are measuring sensitivity for. Typically, it would make sense if we were optimizing our S at t equation to say we want to make t as small as possible. However, since t is our independent variable, we cannot put a restriction on t while we're optimizing it. So our two ways of optimizing our sensitivity equation is by increasing our value of A and by decreasing our value of D. On these slides, we're going to show a graphical analysis of our function of capacitance and our function of sensitivity on the next page. Essentially, to graph these functions, we have to assume two different things. First, we wanted to assume that D is equal to 5 millimeters and that A is equal to 400 millimeters squared. on the left side of Desmos, you can see all of the constants that are used in the capacitance equation, and then you can see the graph of the capacitance function as a function of temperature. So in this Desmos application, instead of using t, we used x, however, they represent the same function, and we can see it's a relatively decreasing function. On our next slide, we are showing sensitivity. Once again, all of our constants are the same and they're defined on the left-hand side of Desmos, and s at x is equal to the derivative of c at x. So we can see that the sensitivity function is actually an increasing relationship. However, the important part to notice is that all of the sensitivity is below the x-axis. So even though the sensitivity equation is increasing, this implies that the capacitance equation is constantly decreasing, but it is going to decrease at a slower and slower rate. And that makes sense because if you look at our capacitance equation, you can see that it is constantly decreasing, while our sensitivity equation is constantly increasing. Now that we've completed our theoretical analysis, we can move on to our experimental analysis. Firstly, we're going to begin by designing a circuit. So on our screen on the left side, we can see a simple voltage divider circuit where we have our voltage, which is a variable V, our capacitance, which is a variable C1, and our capacitance, which is a variable C2. And we've also labeled the point we're measuring V out. The top part extending is the positive of V out, and the bottom part is the negative of V out. So on our side, we wrote that C1 is a known capacitance, and this is true in the sense that C2 is unknown. And since C2 is unknown, we are going to be calculating V out, and using our voltage divider equation, we're going to determine what C2 is equal to. And V out is actually an unknown at the beginning. However, we can calculate this experimentally. Our plan to calculate V out is either using an Arduino or a voltmeter, depending on how our approach is. If we're going to use a DC current system, we can use both the voltmeter and Arduino, assuming that our voltage is less than 5 volts, and if it's higher than 5 volts, we can only use a DC voltmeter. However, if we're going to use an AC current approach or AC voltage approach, we can only use an AC voltmeter. Moving forward, we want to derive electrical signal with respect to capacitance. So in the previous slide, we designed our circuit, and you can see the diagram on the paper on the left-hand side of the screen. Essentially, we replace both of the capacitors with impedances to create a more simplified formula. And I pointed that these impedances both represent capacitance. So the impedances Z1 and Z2 also have a capacitance C1 and C2. And I also labeled where V out is equal to. So we know that Z1 is equal to negative J over omega C1, and similarly Z2 is equal to negative J over omega C2. We also know from our voltage divider equation that V out is equal to Vs, which is the voltage of the source, times Z2 over Z1 plus Z2. Subbing in the known Z1 and Z2 values from above, we can rearrange and simplify our equation to give us that V out is equal to Vs times C1 over C1 plus C2, where our V out is our electrical signal we are measuring, Vs is the source, and C1 and C2 are the capacitance given within the circuit. So thus we can, on the right hand side, we have the equation V out is equal to Vs times C1 over C1 plus C2. And this equation will play a very important part moving forward about measuring our electric signals. And I've also mentioned the meaning of all the variables here, where V out is our electrical signal, Vs is our voltage source, C1 is our known capacitance, and it is important that the fact that it is known, since if this was unknown, it would make our voltage divider circuit a lot more complicated, and that our C2 is our unknown capacitance, and since our C2 is unknown, we can calculate our C2 using our Vs, V out, and our C1, which are all known. Moving forward, we want to calculate the sensitivity of the electric signal. So we just calculated the electric signal with respect to the capacitance C2, which C2 is the unknown variable. And we know that sensitivity is simply the derivative of our electrical signal with respect to our capacitance. And our capacitance specifically is C2, since that is our unknown variable. So on the paper, on the left-hand side of the screen, we can say that our sensitivity with respect to C2 is equal to the derivative of V out, which is our electrical signal, with respect to dC2. And you can see we brought our calculations all the way down and using our quotient rule, and we can conclude that the sensitivity of the electrical signal is given by negative Vs times C1 over C1 plus C2 quantity squared, where S is our sensitivity, V out is our electrical signal, Vs is the voltage source in the circuit itself, C1 is our known capacitance, and C2 is our unknown capacitance. Moving forward, we want to discover the precision for measuring electric signals. So currently we want to see what experimentally could have gone wrong that would have ruined our precision. So after a little bit of research, we can see that the average error on a voltmeter for a 0 to 100 volt reading is plus or minus 3%. For an Arduino, for a low voltage reading is plus or minus 5%. We also have to consider the fact that there are error in voltage sources through noise, or for instance, our voltage source is not outputting the proper amount of voltage by 1/100th of a volt, for instance. Or our capacitor's capacitance may fluctuate from its given value, that is similar to our voltage source, where our capacitance might fluctuate from the given capacitance by 1/100th of a farad. So after all these errors, let's assume that the worst case error is plus or minus 5%. Assuming that our worst case error is plus or minus 5%, we know that our V out, which is a function of our capacitance C2, is given by Vs times C1 over C1 plus C2. However, we said that our minimum error is going to be minus 5%, so our V out minimum has to be 0.95 times Vs times C1 over C1 plus C2, or we can just say 0.95 times V out. Similarly, our V out maximum is going to be plus 5% of our V out quantity, so it is 1.05 times V out, or 1.05 times Vs times C1 over C1 plus C2. And this is our precision for measuring electrical signals. We want to consider the overall sensitivity of our setup. So as you can see on our paper, we have two very important equations. From our voltage divider, we know our V out is equal to Vs times Z2 over Z1 plus Z2. Through our entire process, we also found V out in respect of capacitance, which is equal to Vs times C1 over C1 plus C2, and rearranging this equation, we get that C2 is equal to Vs times C1 over V out minus C1. And this is very important, as our second very important equation is our capacitance as a function of time, which is given as 87.72 times A times epsilon naught times e to the power of negative 0.0045 times temperature all over d. So we know that our C2 value should be equal to our capacitance at t as a function of temperature value for all values. So now we can find what our V out as a function of temperature is equal to by simply letting C2 equal to C at t. So as you can see, we did our rearrangement of equations right there, and we are left with that our V out as a function of temperature is equal to this very big equation, our Vs times C1 times d, all over 87.72 times A times epsilon naught times e to the power of negative 0.0045 times temperature plus our C1 times d. So this is essentially our V out with respect to temperature, and you can see this equation on the right side, outside of the paper, in a more neat format. Moving forward, we can graph our overall sensitivity, our overall V out equation. We have not arrived at the overall sensitivity equation so far. We are currently just finding our V out with respect to temperature. As you can see, our V out equation has a very unique feature, as it starts from a very low value when it's around negative 300 degrees Celsius, and when it hits about 1500 to 22,000 degrees Celsius, we can see that it's asymptotically approaching the value of 5. And on the left hand, I should have mentioned that we have defined some specific constants, where our V1 value is equal to our 5. So we can see that our function is approaching our maximum V1 value, or V source value, asymptotically. And this is a very unique It is a very unique discovery. So essentially, as our temperature increases to very, very high values of T, we can see that our V out as a function approaches our V source. And this is a really unique discovery. Anyways, moving forward, we are trying to find the overall sensitivity. And since we define sensitivity as a function of temperature to be our derivative of V out as a function of temperature over the differential T, we can say by taking the derivative of our V out, which we calculated on our previous page, on the left hand side you can see all the calculations we did specifically using the quotient rule, and we are left with that sensitivity as a function of temperature. Our middle equation on the right is equal to 0.39474 times our voltage source times our C1, which is our known capacitance, times D, which is the distance between the plates, times A, which is the area of the size of the plates, times epsilon naught, which is a constant, times e to the power of negative 0.0045 times temperature, all over the 87.72 times A times epsilon naught times e to the power of negative 0.0045 times temperature plus C1 times D, and the denominator is all squared. Now this is a graph of sensitivity for V out compared to temperature. Note that the domain for V out in this graph is from negative 300 degrees Celsius all the way until 5000 degrees Celsius. In reality, we've exceeded the upper bound of temperature. Sorry, we have not exceeded the upper bound of temperature, but we have exceeded the lower bound of temperature, since the lower bound of temperature is negative 273.15 degrees Celsius. However, for the sake of this graph, we are going to neglect this small detail. We also notice that there is an interesting bump. This interesting bump looks like a hump where it goes upwards and then starts decreasing. This is going to be a turning point for the sensitivity function, as you show right over here. We can see it's increasing, but then it changes the curvature. So this bump in the V sensitivity equation is essentially just showing a turning point in the function itself. However, moving forward, to measure the precision of the electrical signal, we have to consider two different worlds, the theoretical world and the practical world. In the theoretical world, the temperature can vary from anywhere from between negative 273.15 degrees Celsius all the way until 1.42 times 10 to the power of 33 degrees Celsius. This means our rate of change of our electrical signal with respect to temperature, evaluated at 1.42 times 10 to the power of 33, is approximately 0, as we can see in our graph for sensitivity. It is going to approach 0 the further and further you go out. However, in the practical world, for instance, the world we are living in, temperature will vary from at least about negative 100 degrees Celsius until 100 degrees Celsius in a typical day or household. So we do not need to consider more than that extent. So the rate of change of our electrical signal with respect to temperature, evaluated at temperatures negative 100, is approximately 1.0445 times 10 to the power of negative 3. So we're only going to consider the practical world, and we're going to use the value for negative 100, since that's going to be lower than the value evaluated at 100, since that is currently increasing. And as you can see in this graph, the value for negative 100 is lower than any values above negative 100 until 100 degrees Celsius. Moving forward, if we consider the precision of electrical signals, we have our rate of change of electrical signal with respect to our temperature, dV out over dt, and that is given by that equation there. If we rearrange this equation for dt, we're given this equation shown in the second line, where dV out is going to be in the numerator. However, we know that our lowest value is for our dV out is going to be negative 100. So then our dV out is going to equal negative 100, and then we get our dt to equal this approximate value of negative and this quantity of 3.14217416665 times 10 to the negative 12 times e to the power of negative 0.0045 times temperature plus 2.5 times 10 to the power of negative 14 quantity squared all over 1.747551046 times 10 to the power of negative 28 times e to the power of negative 0.0045 times temperature. Thus, we can conclude the smallest change in detectance that can be measured will depend on the value t itself, as we can see by the dt approximate equation. About this presentation, which talks about practical considerations and limitations of our device. There are essentially 6 main practical considerations that we have to be wary of. The first one being the containing the fluid between the parallel plates. So as we mentioned earlier, we're planning on containing the fluid with either glass or polystyrene. However, we can also use other materials. But the problem is we have to take into consideration of the water evaporating, the water leaking, and the water expanding. Because if the water expands, it could break the sensors and it can break the surrounding barrier. So we have to make sure we have a proper amount of fluid. We have to make sure that the barriers on the side does not increase the conductance of the parallel plates itself, and we have to make sure that the evaporation does not destroy any of the parts surrounding it. So containing the fluid between the parallel plates is probably going to be one of the bigger practical considerations. The second really huge one is the accuracy of minute temperature changes. We did calculate the precise electrical signal differences that it can calculate in 2 slides before. However, a very important part is if there is a temperature change of 0.5 degrees Celsius, will our sensor be able to pick it up? And there is one solution that we came up with, which will be presented in a few slides later. Another one is fringe field. Fringe field is going to be a practical consideration for any parallel plates problem. We typically neglect fringe fields in any theoretical calculation for parallel plates. However, we do have to take into account for them while we're doing them while we were working with parallel plates in real life. Another practical consideration is the effectiveness of the voltmeter. As brought up before, for instance, let's say we have a 5-volt DC voltmeter. If the voltmeter is outputting approximately 4.95 volts, and we're doing our calculations based on 5 volts, it is going to influence our theoretical calculations, which could mess up our sensor, and that will cause multiple problems. Another practical consideration is the size to maximize the efficiency and minimize space taken. What I mean by this is our parallel plates and our water in between to optimize this, we need to increase the A value and decrease the D value, but we can only do to a certain extent. We can't make the A value the size of the entire room, and we can't make D so small that the parallel plates are touching each other. So we need to find the value of A and find the value of D such that the parallel plates are at an optimal distance. And the last point is the voltage source fluctuations, which was also talked about in the effectiveness of the voltmeter. So relating back to the voltmeter, we can say that, for instance, if a voltmeter picks up measurements wrong, we have to take into consideration for our V out value. So these are all just small things that can add up and influence our final results at the end of the day. However, we are hoping that our values are accurate and that we can get as close as possible, which will give us the greatest results. Moving forward, there are also some roadblocks that took into consideration. I did mention this in the previous slide, fringe field's influence on material. For instance, we were talking about glass versus polystyrene. Glass has a higher dielectric constant than polystyrene, which means if fringe fields are going through glass, it would highly influence the results of the capacitors, which means our calculations for our capacitance will be incorrect. That's why we also took into consideration polystyrene. Polystyrene has a lower dielectric constant, almost that of air. It is probably twice as much as air, while glass is almost 6 to 8 times more than air. So since by reducing the value of our dielectric constant, yes, polystyrene will still contribute to the capacitors, however, the polystyrene will contribute less and will have more accurate measurements. And the second roadblock is the water evaporating from the system. For instance, the volume of the fluid and the humidity. So if we have a hole in our system such that water can escape or increase, That means the amount of liquid and fluid or gases or frozen material we have within our systems will increase and decrease. And this increase and decrease will highly change our dielectric constant, since we're having more material and less air and more water, so on and so forth. And this will alter the dielectric constant. So we need to find a way to keep the water, a constant volume of water between the two parallel plates constantly. Our proposed solution for all of our practical considerations and our roadblocks are ranges. Essentially, we're going to have a range of values for our capacitance where it is just right. And in this just right range, as indicated in the middle of the slides, we're going to turn off the AC or the heater. And then we're going to have a range where the capacitance is too low. Essentially, when the capacitance is too low, we're implying that the dielectric constant of the substance inside is too low, since capacitance is equal to A times epsilon over D. So if epsilon is too low, this implies that the temperature is very high. And if the temperature is too high, we're going to turn on the AC. And same with our opposite logic, if our capacitance is too high, this implies that our dielectric constant is too high, which implies that our temperature is too low. Therefore, we turn on the heater to make it warmer. So instead of having very precise measurements, we can have critical ranges, and specifically the critical range of having our capacitance just right, our capacitance too low, and our capacitance too high. Alright, this is the last slide. We covered the description of my sensing application, the practical considerations, the experimental and theoretical analysis, and we went into detail with mathematics and graphs. So thank you for listening to my presentation. I really hope you enjoy. Feel free to contact me if you have any more follow-up questions. My email and my phone number are written in the slides. Thank you and have a great day.